Welcome to fifth episode of our podcast series on the fascinating world of quantum mechanics. In this episode, we will explore one of the most intriguing and counterintuitive concepts in quantum mechanics, quantum entanglement. Quantum entanglement refers to the phenomenon where two or more particles become connected in such a way that the state of one particle is dependent on the state of the others, even when they are separated by large distances. The theoretical basis for quantum entanglement was first proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in a 1935 paper. They argued that quantum mechanics predicted the existence of spooky action at a distance, where the state of one particle would instantaneously affect the state of another particle, violating the principle of locality. However, it was not until the 1960s that experimental evidence for quantum entanglement was obtained. The first experiment was conducted by John Bell in 1964, who proposed a test to distinguish between the predictions of quantum mechanics and classical mechanics. His test involved measuring the correlation between the spins of two entangled particles, and he found that the results were in agreement with the predictions of quantum mechanics but not classical mechanics. Since then, numerous experiments have confirmed the existence of quantum entanglement, including the famous EPR, Einstein-Podolsky-Rosen, experiment, which demonstrated that entanglement could occur even for particles that were far apart in space. Let us briefly talk about the EPR, Einstein-Podolsky-Rosen, experiment. This is a famous thought experiment in quantum mechanics that was proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. The experiment was designed to challenge the predictions of quantum mechanics, specifically the idea of quantum entanglement, which Einstein famously referred to as spooky action at a distance. The experiment involved two entangled particles, such as electrons, which were separated by a large distance. The results of the experiment showed that the properties of one particle were dependent on the properties of the other particle, even though they were far apart, confirming the existence of quantum entanglement. Quantum entanglement has profound implications for the field of quantum communication and quantum computing. For example, in quantum cryptography, entangled particles can be used to transmit information securely, as any attempt to intercept the message would be immediately detected. The implications of quantum entanglement are also at the heart of the paradox known as Schrödinger's cat, which illustrates the strange and seemingly contradictory nature of quantum mechanics. In this thought experiment, a cat is placed in a box with a vial of poison that will be released if a radioactive atom decays. According to quantum mechanics, until the box is opened and observed, the atom is in a state of superposition where it is both decayed and not decayed. This means that the cat is also in a superposition of being both alive and dead. It is only when the box is opened and the state is observed that the superposition collapses and the cat is either alive or dead. In conclusion, quantum entanglement is a fundamental concept in quantum mechanics that continues to fascinate scientists and inspire new avenues of research. Its mysterious nature and potential for groundbreaking discoveries in physics make it a topic that is sure to capture the imagination of anyone interested in the mysteries of the universe. Next episode is on teleportation. Do subscribe to keep yourself updated. Thank you for listening to our podcast. If you have any questions or suggestions for future episodes, please feel free to leave them in the comments or reach out to us on social media.